This is my fourth video on elastic collisions in 2D. Here's a question, give it a go and come back when you're ready. We've got a pretty bland diagram here, so I'm just going to add a few labels just to start off. We may end up needing them, we may not, but I always think it's a good routine. Okay, so we don't know this angle, so I'm going to call it alpha. You can call it whatever you like, but I'm going to call it alpha. And we don't know the velocity after the first or second collision, but I'm just going to start off by calling the velocity after the first collision v, like so. Now, we're dealing with kinetic energies and we're not given a mass, so we're just going to make up the mass to be m. And we can do this because it's a percentage question. Okay, we're dealing with percentages and the mass always cancels out in questions like this. So it doesn't matter if the mass is 10 kilos, 2 kilos, whatever. Okay, we're going to call it m because it's going to cancel out. So the initial kinetic energy, okay, the initial kinetic energy is going to be equal to the half times the mass times the initial velocity squared. Okay, so that's our initial kinetic energy. Let's do some resolving to try and work out our final kinetic energy. If we resolve parallel to the wall AB, we get that u cosine of 60 is equal to v cosine of alpha, using our labels v and alpha. And if we resolve perpendicular, remembering to times by e, we get that e u sine 60 is equal to v sine of alpha. Now we can work out v by taking the square root of v cosine alpha squared plus v sine alpha squared, like so. And that's equal to the square root of u cosine 60 squared plus 1 over the square of 3u sine 60 squared. Now that gives us root 2 over 2u. We can now go back to our diagram and replace this v with what we know it's equal to in terms of u, root 2 over 2u. Also, one important thing to notice is that these are the parallel and perpendicular components with respect to AB, and let's just mark these in to help us out. So u cosine 60, well, cosine 60 is a half, so the parallel component is a half u, and 1 over root 3 u sine 60, well, sine 60 is root 3 over 2, so 1 over root 3 times root 3 over 2 is also a half, so the perpendicular component is also a half u. Now when we're looking at its second collision, now with BC, the component parallel to BC never changes. So we know that this component here is also going to be a half u because it was a half u in the beginning down here. And we know that the perpendicular component was initially a half u, but we have to times that by the coefficient of restitution, which we know with BC is root 2 over 5. So that's a half times root 2 over 5, which is root 10 over 10u, and that's coming out of the wall. So to find the actual final velocity, which I'm going to call w, we just need to take the square root of those two squared. So that's the square root of root 10 over 10u squared plus a half u squared. Okay, and when we do that, we get root 35 over 10u. So that is the final velocity after both collisions. Now let's work out the final kinetic energy after both collisions. Okay, well that's just going to be a half times m times the final velocity squared, which we've called w, which is a half m root 35 over 10u squared, okay, which is a half mu squared times 0.35, okay, because this number squared is 0.35. And that has proved that it is 35% of the initial kinetic energy, like it's asked. So this is quite an easy question. You just have to do a bit of resolving, and it's quite nice and easy because the walls are perpendicular. Let's have a look at part B. It says, in reality, the floor and the walls may not be smooth. What effect will the model have had on the calculation for the percentage of kinetic energy remaining? So this is a nice easy one, and these are really common 1 markers in mechanics questions. And if the floor and the walls aren't smooth, more energy loss is going to occur. Okay, so we would say it would decrease my answer due to resistance causing energy loss.